welcome you all in the fourth lecture of Electronics Measurement and Instrumentation. I, Dr. Indu Prabha Singh, Professor, Department of Electronics and Communication Engineering, Shri Ram Swarup Memorial Group of Professional Colleges, Lucknow, here to present fourth lecture that is based on the topic of transistor voltmeter circuit. So, here I will discuss the electronic voltmeter, emitter follower electronic voltmeter, and what is the limitation of emitter follower transistor, then practical emitter follower transistor voltmeter, and then next is emitter follower transistor voltmeter with FET, and then I will discuss the operational amplifier voltmeter. So, what is the advantage of electronics voltmeter and why do we need electronics voltmeter? Actually, we can measure any voltage by using a simple PMMC instrument. So, we can measure the PMMC instrument voltage. So, what is the disadvantage of using the PMMC instrument? So, the disadvantage of using PMMC instrument that these instruments are not able to provide a very high input resistance. So, here and in this lecture I will discuss only the voltmeters, electronics voltmeters that are used for the measurement of DC voltage. So, suppose we are using an PMMC instrument. So, suppose we are using this is suppose a resistance, suppose the value of resistance is 1 kilo ohm and we are using an instrument, an electrical instrument which has input resistance of suppose 100 kilo ohm. So, suppose if we connect a 100 kilo ohm voltmeter which is having an input resistance of 100 kilo ohm. So, what will happen? The voltage across this resistance. So, here it is 100 kilo ohm resistance, input resistance of voltmeter is 100 kilo ohm and here the input resistance is 1 kilo ohm. So, what will happen? This 1 kilo ohm resistance, the voltage drop across this. So, maximum current will flow through this resistance, only a very small amount of current will flow through this 100 kilo ohm resistance. So, what will happen? This meter will give a very high accuracy with the measurement, because it does not have a loading effect on this meter, this resistance. But suppose if we are using a meter that is having only the value of 1 kilo ohm, then what will happen? This current, the current that is flowing through this resistance will divide into two parts and only the 50% of voltage we will get by this meter. So, this is known as the loading effect. So, we need to avoid this loading effect. So, to avoid this loading effect, what we are doing previously in previous lecture I have discussed this, कि we are using a very high value of resistance in series with this PMMC instrument, so that the maximum voltage drop across that resistance and so very less voltage will appear across this meter. If we are using a very high value of resistance, then what will happen? The maximum energy drop is across that resistance and then that produces a heat and which will also reflect the measurement of the this PMMC instrument. So, this electronics voltmeter has a very good value that it offers a very high input resistance. So, when we are using any electronics component like we can use a transistor, we can use a FET, MOSFET or op amp. So, it provides very high input resistance. The second thing, if suppose the voltage which we want to measure is having a very low value, then we can also amplify that voltage by using these devices. Second and third thing is that in this PMMC instrument which is used for the electrical measurement, then the instrument movement, the deflection also draw the power from that current only, that voltage only which we want to measure. But in this meter, in this electronics meter, we are supplying a different power supply to the circuit. So, the power is not drawn from the meter. third is we can use a very small value of voltage by using this meter because we can amplify that signal. So, generally we are using emitter follower transistors for the voltmeter circuit. So, basically transistors, we are using a transistor because it offers very high input resistance. So, transistors we can use in 3 configuration, that is common base, common emitter, common collector configuration. So, different configurations are having different characteristic. So, here we are using the characteristic of common collector configuration CC. So, common collector configuration, that is also known as emitter follower. So, in common collector configuration means we are taking output from the emitter and this collector is kept constant, collector is kept common between input and output. So, in common collector, in common base, common emitter configuration, we are taking output from the emitter terminal, from the collector terminal, but in this common emitter follower transistor voltmeter, we are taking output from the emitter terminal, and this is known as emitter follower because the emitter is following this current IB. So, there is a relationship between IE and IB, that IE is equal to 1 plus HFE, we can say HFE into IB, or we can say 1 plus beta into IB. So, this IE current, emitter current is following the base current, that is why this meter is known as emitter follower voltmeter. So, here we are using transistor because transistor offer a very high input resistance, and when it is used in common collector configuration or in the emitter follower configuration, then its input resistance all further increases. And the second thing is that common collector configurations, the voltage gain is 1 and it offers very high current gain, because current gain is the output current IE divided by IB, and it is approximately equivalent to 100. So, now if we see this circuit, so meter current is equal to emitter current of the transistor, because the emitter current is flowing over here, and this Rm and Rs, Rs is the series resistance of the emitter, series resistance of this PMMC instrument, and Rm is the internal resistance, that is the coil resistance of the meter. So, this meter, if we are not using this circuit, the input resistance of this meter will be Rs plus Rm. But when we are using this circuit, when meter is placed at the emitter, then what will happen? The V input is equal to, if we consider the V input is equal to this voltage drop VBE plus VE. So, where VE is equal to emitter current, that is the meter current, into Rs plus Rm. So, V input is equal to VBE plus VE, where VBE is plus this Vm is equal to VE is equal to IE Rs plus Rm. Now, the current IE we can find out from this. So, IE is equal to V input minus VBE divided by Rs plus Rm. So, meter current, if we find out the relationship between meter current, because it is the emitter current of the circuit. So, this meter current is equivalent to the emitter current of the transistor, and it is equivalent to 1 plus HFE, where HFE is the gain of the amplifier, current gain of the amplifier, and into IB. So, if we can since the value of HFE is very high, it is approximately 50 to 150, in between 50 to 150. So, we can ignore this one. So, it is Im, the meter current is approximately equivalent to the HFE into IB. Now, the input resistance offered by this meter will be input current, input voltage divided by input current, that is V input by IB. So, this is the input resistance. So, we can see the IB current is very less with respect to IE current. So, the input resistance is approximately increased by 100 times by using this transistor. The drawback of this meter, this emitter follower meter, is that there is a drop of 0.7 volt between the base and emitter of this transistor. So, that is approximately, if we are using silicon transistor, then it is 0.7 volt. So, we are unable to measure less voltage than 0.7 volt. So, this is the main drawback, and again if we want to measure 1 volt, if the input is 1 volt, then again across the meter it will reach only 1 volt minus 0.7 volt, that is 0.3 volt. So, this meter will only measure the 0.3 volt. So, that is the main drawback of this meter. Now, we can understand this drawback by seeing this example. The example is a simple emitter follower circuit has VCC, that is a supply voltage of 10 volt, and this RS plus RM is 9.3 kilo ohm. Full scale deflection current IM is 1 milliampere and transistor HFE is 100. So, first we have to calculate the meter current when V input is 5 volt. So, when V input is 10 volt, okay, then second thing we have to determine the voltage of input voltage with and without resistance. So, as we know that the input voltage is 10 volt. So, at 10 volt the meter current will be okay, meter current at first we calculate the meter current at 5 volt. So, when the input voltage is 5 volt, then the meter current IM is equal to V input minus VBE divided by this resistance. So, it is 5 minus 0.7 divided by 9.3 into this is 10 to the power 3. It is not actually 10, it is 10 to the power 3. So, it is 10 to the power 3. So, it is it will be 0.462 milliampere. So, when the input current for 10 volt is 1 milliampere, so it should be 0.5 milliampere for 5 volt input, but here it is 5 for the 5 volt input the current is 0.462 milliampere. So, it means the current is reduced because of this voltage drop. Similarly, input resistance, if there is no transistor, then it is equivalent to the series resistance plus the meter resistance, that is 9.3 kiloampere. But the input resistance when we are using this transistor, then IB is equal to IM by HFE, that is 0.462 milliampere divided by 100. So, it is 4.62 microampere. So, when we find out the input resistance, then it is Ri is equal to V input by IB, and it is 5 volt divided by 4.62 microampere. So, it is 1 mega ohm. So, you can see that the input resistance because of using this transistor is increased by 100 times. So, that is the advantage of this transistor, this meter, electronics meter. So, limitation, as I have already discussed, when V input is 5 volt, the meter current should be 0.5 milliampere, but it is now 0.462 milliamperes. That is the main drawback of this meter, because here is a voltage drop of 0.7 volt. So, because of this 0.7 volt drop, the deflection is not proportional. So, to remove this drawback, we are using this type of configuration. This is the practical emitter follower circuit. So, here we have used two emitter follower circuits, two common collector circuits, and the meter is placed between the emitter of both the transistors. So, what will happen, and this resistance, there are three resistances R4, R6 and R5. R5 is a variable resistance, and by varying this value of R5, we can adjust the 0 of this meter. So, before using this meter, we have to adjust the 0. First of all, this pointer should show the 0 position. So, what we will do, without applying any input, we are not applying any input, then what will happen, since this terminal is grounded, so voltage at this point is 0 volt. Okay. So, this base of this Q1 transistor is at 0 volt. We know that VBE, base to emitter voltage of transistor, is, if it is a silicon transistor, it is a 0.7 volt. So, what will happen, base is at 0 volt, but the emitter is at 0 emitter voltage VE of this meter, that is VE1. So, VE1 is equal to 0 minus 0.7, that is minus 0.7 volt. So, here the VBE1 is 0.7 volt is at this point. Okay. And now we are seeing that this meter will not display any value, it means the meter will show 0. So, meter will show 0 at this position when the voltage drop across this point and this point should be equal. So, when VE1 is 0.7 volt minus 0.7 volt. Okay. So, this potential at this point should be minus 0.7 volt. So, when at both terminal, suppose this is point A and this is point B. So, when there is no potential difference between A and B, the meter will show 0. So, at that time the voltage, potential voltage at A point is minus 0.7 volt and voltage at this point is also minus 0.7 volt. Now, if we apply any voltage, suppose we are applying 1 volt at V input, then what will happen? At this point there is 1 volt now. Okay. There is now 1 volt. So, what will happen at point A? The voltage at point A will be VA, voltage at point A will be 1 minus 0.7 volt, that is 0.3 volt. Now, the voltage difference between A and B, because the meter will deflect only the difference between these two. So, the difference between V and A, that is VAB. So, what it will be? 0.3 volt minus, there is voltage is at minus 0.7 volt minus 0.7 volt. So, what will happen? It will be 1 volt. So, whatever voltage we are applying here, the same voltage will appear across the PMMC meter. So, PMMC meter will display the voltage that is equivalent to the input voltage. So, by using this meter, we using this practical emitter follower transistor voltmeter, we can measure the exact value of the voltage. Here we are also applying VCC and VEE. So, this meter is not drawing any current from the circuit, and the input resistance of this meter is also equivalent to the previous meter, because this is placed at the emitter of this given transistor. So, this is multiplied by the HFE. So, input resistance is increased, there is no voltage drop across the meter. So, whatever we are applying at the input, the same reading we are getting at the from the meter. So, that we can also see from this example, that this is a circuit where R2 is equal to R3 is equal to 4 ohm, 4 kilo ohm, and supply is plus minus 12 volt. Calculate the meter current when V input is 1 volt and V input is 0.5 volt. So, we know that voltage drop across this base to emitter is 0.7 volt. So, if V input is 1 volt, so when V input is 1 volt, so what will happen? This VE1, this voltage will be 1 volt at this. So, 1 volt minus here at this time the voltage is 0.7 volt. So, 1 minus 0.7 volt, that is 0.3 volt, and VE2 is minus 0.7 volt, as I have already told you. Then V is equal to VE1 minus VE2, that is this 3.3 minus 0.7, that is 1 volt. So, current at this time is equal to 1 V by 1 volt by 4 kilo ohm. So, it is 0.02 0.25 milliampere, whereas in previous lecture we have seen the current is reduced. Similarly, if we reduce the voltage by 0.5 volt, then VE1 that the voltage at this emitter is 0.5 minus 0.7, that is minus 0.2 volt, and VE2 is already at minus 0.7 volt. So, the voltage across this meter is the difference of these two, that is minus 0.2 minus minus 0.7. So, it is 0.5 volt. So, the exact value whatever we are applying at the input, that voltage appears across the meter. So, the meter will deflect the same current. The current through the meter is 0.5 volt divided by 4 kilo ohm, that is 0.125 milliampere. So, the current is not reduced, the same current is flowing through the meter, and so meter deflect the same value of voltage. Now, that was the meter that we can use for a single voltage. If we want to increase the range of voltages, suppose we want to measure from 0 to 200 millivolt, then we want a second range that should be 0 to 100 volt, or the third range 0 to 1000 volt. So, for this, if we want to use a multi range, we want to convert this electronics voltmeter into multi range meter, then we will use an attenuator. So, this is the attenuator, means a combination of resistances. In AC circuit generally, since it is a DC circuit, so we are not using capacitor, we are using only resistance. So, here suppose this is the value of resistances, and suppose the maximum deflection voltage that is required for the meter is 1 volt. So, the meter should not, the voltage that is applied across the meter should not reach value beyond this 1 volt. So, what will happen, suppose this meter is at this potential. So, we can see that a voltage divider network, we know that in a voltage divider network, suppose there are two resistances, and suppose input is applied over here, input is at this E, and suppose the voltage at this point is V. Okay. So, this one is R1 and this one is R2. So, the voltage V is equal to the voltage across the resistance, V is equal to the resistance across which we want to measure the voltage, and divided by the total circuit resistance. So, it is divided by R1 plus R2 into E. So, this is the voltage divider rule. So, here when meter is placed, this selector switch is placed at this position, then what will happen? The total resistance, we want to see the voltage across these two resistances, 60 kilo ohm and 40 kilo ohm. So, the current, the voltage across this meter will be RC plus RD, these two resistances divided by the total resistance. So, it is the input voltage is suppose 10 volt, because this switch is showing 10 volt. So, 10 volt divided into 60 plus 40 divided by total resistance. So, again it will be 1 volt. Similarly, if we place this at this position, so it will be 40 kilo ohm divided by total 1000 kilo ohm. So, it will again be 25 volt and it will be 1 volt. So, this is the range selector switch, and when we want to convert our meter into multi range meter, then we are using this selection switch. So, this is the circuit of practical emitter follower circuit, and here we are using a FET transistor, because this BJT is also increasing the voltage, increasing the input resistance of the meter, but when we are using FET, so this resistance, whatever the resistance that is at the base of this transistor is again multiplied by the resistance of this FET meter. So, this resistance is also increased, and the resistance value is approximately 1 mega ohm to 10 mega ohm when we are using FET, and this is the deflection switch, the attenuator. So, input attenuator, by this we can select any switch, then by FET amplifier and this transistor amplifier we increase the input resistance of the meter. If we want to measure a very low value of resistance, then we can use the amplifier circuit, and in place of attenuator we can use the amplifier circuit. So, that amplifier circuit can amplify the signal and we can measure the signal. So, this is the same as the previous one. Here we are using input attenuator, then FET field effect transistor input stage is added, so that the input resistance should increase, so that it does not have a loading effect of the previous circuit. Now, similarly, we have used the FET transistor, we have used the BJT to increase the input resistance of the circuit. But we can also use the amplifier, and we can also amplify the signal by using this. So, this is our amplifier voltmeter. So, here as we know, this op amp is used as an amplifier, and the gain of V output, this V output of this amplifier, V out is equal to 1 plus this resistance, feedback resistance, that is R 4 by R 3 into input resistance, input voltage. So, this input voltage is amplified by this time 1 plus R 4 by R 3. So, whatever range we want, that meter can measure. So, we can increase the range of this input voltage, we can increase the input voltage by proper selecting of R 4 and R 3 value, and then that output is fed to the meter. So, meter will deflect according to that value, but here since we have amplified the input signal, input voltage. So, we have to calibrate the meter scale in such a way that it should represent the value of E only. So, okay, that is from my side. Thank you all.